Welcome everybody to another edition of the SIBA webinar series. We're very happy here to have Agostino Capponi from Columbia University, who will talk to us about the adoption of decentralized exchanges. Now, the way we're going to do this is that Agostino will present for somewhere between 45 to 60 minutes. I will interrupt him 3 times after the literature, after the model, and before he presents some empirical validation for his model. And at each of these points, I'm going to ask him some questions. I'd like to encourage you to put some questions in the Q&A. His co-author Ruji may answer some of these questions as we go along, but it would be great if you could put some questions there so that, if there's some clarification or some things that interest you, put it there. And that aside, we will then at the end, we'll give you the opportunity to unmute yourself and ask a question also in person. So with that, again, welcome Agostino. It's been great and we're happy to have you. And why don't you start by sharing your screen and proceed with your presentation.
Okay, thank you so much, Andreas, for the introduction. And of course, thanks to all the CBR organizers for giving me the opportunity to present here. I'm really honored and very pleased to share research on the adoption of decentralized exchanges. Let me share the slides. Can you all see the slides?
Yes, it's all there.
Perfect. Okay, so let me make the big screen. Good. Okay, so this is joint work with Rizeha, who is also here, and he will help me answering questions. And that's about the adoption of decentralized exchanges on blockchain. So I'm going to provide a brief background, then set up the model, then show what results we get, and then discuss some empirical findings which validate some of the testable implications which come out of the model. Okay, I think a brief introduction to blockchain. I think most of the people in this audience, I'm sure they already know even better than me what blockchain is, but just to be on the same page. So blockchain is essentially a decentralized database, a decentralized ledger, where nodes are essentially storing a copy of the entire history of transactions as soon as these transactions are mined and appended to blocks. So what happens is that any users who want to submit transactions to the blockchain will specify the transaction and will also attach an execution fee. And these fees will be essentially taken into consideration by the miners or the validators, who, when they get the right to update the ledger, for example, after solving a computationally costly problem, if we are thinking about the proof of work protocol, they will select the transactions which have the highest fee first, and they will add them into the blocks. So in order to gain priority in the execution, you need to attach a larger fee. I think blockchain has evolved over the years. Like when it first started, they said it was mainly a system to support payment in cryptocurrencies. For example, Bitcoin blockchain is an example of a first generation blockchain, where the objective is essentially to support transactions in Bitcoin or different cryptocurrencies. And typically you specify like a source of a destination. So Alice wants to make a payment to Bob. It will route this payment through the blockchain network. Since then, we have observed an evolution of blockchain, which moved from simply being an infrastructure to support cryptocurrency payments to being a more broader infrastructure to support a large range of financial transactions. What has enabled this transformation or this transition are the smart contracts. So smart contracts are essentially algorithms which are designed to be run on blockchain, and they are running according to specified conditions which are decided by the parties. For example, I might specify that I want to execute a transaction where I want to swap Bitcoin token for an Ethereum token only if the price of Bitcoin token relative to the Ethereum token is above, let's say, a specific percentage. So that means that once my transaction is selected for execution, it will only be executed if this condition is satisfied. In that sense, the contract is smart in the sense that it adapts to the current market conditions on the blockchain. And these smart contracts are being used to implement a very large range of financial services. In fact, there has been a word that has been coined to denote all these financial transactions which happen in a completely decentralized fashion because they run on the blockchain, which is DeFi. So DeFi basically supports lending borrowing transaction where you basically deposit funds to a pool, and then anybody who wants to borrow will be able to interact with the smart contract of the pool and get funds at a specific interest rate. There are insurance services, and there are, of course, decentralized exchanges, which are a large fraction of the entire DeFi ecosystem. In fact, if we look at a picture of the DeFi ecosystem as of last September 2021, we see that DeFi is a large market. It's like around 66 billions, and roughly half of it is accounted for by decentralized exchanges. So it's really a significant market that has been growing more and more over the last year or so. Let's just compare centralized versus decentralized exchange. Many of you are in the students who have worked in market microstructure. They know very well how centralized exchanges work. So here we have typically buyer and seller. They want to trade and they want to transact. So what they have to do is they have to submit their buy limit order or their sell limit orders to an exchange. They cannot do it directly, but they have to do it through a broker. So the broker will take care of passing the transactions to the exchange, and then the exchange will match this buy limit and buy sell and sell limit orders, and the transactions will be executed. So the market makers are these financial intermediaries who decide on the prices. So they specify what's the bid-ask spread at which the transaction needs to be executed. When we think about, and of course, exchanges are for-profit corporations, so they are subject to compliance and governance regulations. When we think about decentralized exchange, which are the exchanges which run on the blockchain, the exchange is replaced by a smart contract, and both the buyer and seller do not interact anymore with the broker, but they have direct access to the liquidity which is available through the smart contract. So it eliminates somewhat this additional step of going through a broker, and the prices are decided by the so-called automated market maker, which is, as I will describe shortly, it's implementing a pricing function which determines exactly the rate at which these transactions are executed. Anybody wants to provide liquidity, acts as a liquidity provider, and he can just deposit those tokens into the smart contract. And there are plenty of liquidity providers. They are not absolutely specialized financial intermediaries, but they are like professional market makers. They can just interact with smart contract and deposit tokens. So anybody can really be a liquidity provider. The basic idea of a decentralized exchange is to crowdsource of liquidity, so to pool liquidity together. So what the liquidity providers are doing are not really competing with each other, but they are somewhat sharing the gains and losses that, that derive from depositing those tokens in the exchange. For example, if we think about Uniswap, Uniswap is the largest decentralized exchange. They handle a pool where you can any investors, any liquidity demanders can swap tokens, token pairs. For example, if there are currently 100 token A and 10 token B in the pool that have been deposited by these liquidity providers, if I am an investor, if I want to get liquidity, what I can do, I can swap token A for token B or vice versa. Right? So I directly interact with the smart contract and I take out some token A for token B or vice versa. This is, of course, an alternative to doing two transactions. For example, first swapping token A for some fiat currency and then using the proceeds from these fiat currencies to buy token B. For example, I don't have to, if token A is Bitcoin, token B is Ethereum, I can directly swap Bitcoin for Ethereum without going from Bitcoin to dollars and then dollars to Ethereum. Okay, so as I mentioned, really anybody who owns both tokens is allowed to be a liquidity provider, right? So really, it's not only designed for professional investors or professional market makers, but anybody really is allowed to provide liquidity. And what happens is that after you have provided liquidity, you become like a shareholder of the pool. So you get pool tokens, and these pool tokens will be used to claim shares of the pool at the time where you decide to exit. For example, if the pool is currently 100 token A and 10 token B, and you are a liquidity provider and you want to deposit, you have to, first of all, deposit according to the ratio of token A and token B that you observe in the pool. So that means that if you want to deposit 10 token A, you have to put 1 token B because the ratio of token A to token B is 10 to 1. If you do that, you will get 4 pool tokens, right? Because you are basically holding 1/11 of the entire share in the pool. So that means that at the time where you exit the pool, you will get 1/11 of the entire amount of reserves that there are in the pool at that time. Okay, so now it comes to the point of defining what is the price at which these transactions are executed. And the algorithm or the smart contract which implements this pricing function is called the automated market maker. So what the automated market maker does is essentially making sure that before and after the trade, a specific function remains constant. For example, if we have, let's say, 100 token A and 100 token B, and a new transaction occurs where a liquidity demander wants to exchange token A for token B, so he deposits in the pool 5 token A, so that the number of token A in the pool goes from 10 to 15, and he wants to take out token B, so the number of token B in the pool decreases. But the key condition that needs to be satisfied is that the value of the function at the reserves before the trade and after the trade needs to remain constant. For example, if the function that is being implemented is the product function, that means that if we have 100 tokens, well, if the value of the function is 100 before the trade, because there are 10 token A and 10 token B, after the trade, when you deposit 5 token A and we took out token B, we need to make sure that this product is also 100. So in order for this to happen, it means that the number of token B that you get out is really smaller than 5, than the amount of tokens that you deposited. In this specific example, is essentially 3.33. So what this is saying is that the trade has a price impact. So this is basically replacing the price impact that we have in traditional market microstructure model with the price impact which derives from the convexity of the pricing curve, which is being chosen by the smart contract. So the more convex this curve is, and the larger will be the price impact, which means that you will basically lose more when you trade or when you swap tokens. For example, if you had 0 price impact, it means that you had a straight line. In that case, if you want to deposit 5 token A, you can take out 5 token B. But the more convex the curve is, the larger will be the price impact. And this is a very important consideration to take into account when you decide to trade. Okay, next question is, okay, why would a liquidity provider deposit in the first place? So what is his incentive to deposit tokens in the pool? And this incentive is essentially to gain from the fees of anybody who wants to trade. So that means that if you are a trader, you want to swap token A for token B, you want to deposit 10 token A and you want to extract 1 token B, you can do that, but you have to pay a fee which is proportional to the amount of token that you are depositing in the pool. So in this case, you want to take out 1 token B, you deposit 10 token A, you have to pay a fee which is basically a percentage of 10. The current fee that is charged by Uniswap is around 0.03%, right? So this means that you multiply this 10 by 0.03%, effectively creating tokens which are added to the pool. So it's like as if instead of 10 token A, you are essentially putting in the pool more than 10 token A, which is good because at the time where you decide to exit, you will get a larger amount of reserves, like for the same number of pool tokens that you hold. Okay, now I want to basically summarize the main characteristic that I have illustrated up to now. So, and this is also very important to understand the results that we will show later in the talk. First, I think blockchain settlement, the way that the orders are processed, plays a very important role. Remember that the orders who are processed first are those who have higher fees attached to it. So it's essentially bribing the validators is really the key point. So if you want the transactions to be executed quickly, you would have to attach a larger fee. Second, there is this mechanism of liquidity pooling. So liquidity providers are essentially all participating and crowdsourcing liquidity, and they are all claiming a share of the entire pool at the time where they want to exit. Second, a third important characteristic is that the pricing function is deterministic, is set up by exogenously by the automated market maker, and there is no need to match buy and sell limit orders. So you directly interact with smart contracts, you swap tokens directly based on the curvature of the function. Okay, so let me discuss what results we want to show in this paper. So what we want to really demonstrate is that this adoption of decentralized exchange is not guaranteed to happen. And the reason why it's not guaranteed to happen is because there are arbitrageurs who can extract rent from the liquidity providers. And the reason why they can extract this rent is essentially, one, the fact that the blockchain friction of processing orders based on high fee transaction is essentially preventing liquidity providers from potentially exiting the pool when they would like to do that. And second is because each liquidity provider is not the entire shareholder, it's not a monopolistic shareholder of the pool, but the pool is basically crowded and the liquidity is shared among a large number of liquidity providers. Because there is this possibility of arbitrage, then what we see is that the cost of providing liquidity goes up to a point where there could even be a liquidity freeze, which means a situation where none of the liquidity providers want to deposit. Here, I would like to clarify that liquidity, I mean really the amount of tokens that are deposited in the pool. And as a consequence of that, because there is this competition for exploiting arbitrage opportunities, the amount of fees that will be bid on the blockchain will go up, imposing negative externalities on other users of the same blockchain. Because if I want to use blockchain to make a payment transaction, if there is this high competition by arbitrageurs, I will have to pay an even larger fee if I want my transaction to be executed relatively soon. And then we will demonstrate how we can mitigate this arbitrage problem. We will not be able to completely eliminate it, but we can somehow achieve the trade-off between minimizing the arbitrage rents that are being extracted from liquidity providers, and at the same time incentivize enough liquidity providers to provide liquidity. I think this is a good point to stop. Yes, for questions.
So I've not seen any questions here currently in the chat. But obviously, this is something that I'm also interested in, simply because, and I'm sorry, my webcam just died. Obviously, I've been working on this too, and I find this interesting by itself. Hold on, there's a question here. Let me just read out the question from Rafael.
Yep.
It is liquidity or stake in a pool? Liquidity is related to trading volume, and here we talk more about the holdings of tokens.
Yeah. So here, I think it's a good point. Here, by liquidity, I really mean the tokens that are deposited in the pool, as I clarified earlier. So I'm not looking at like volume or value. Of course, if there are more tokens deposited in the pool, it means that there is also a larger volume of trades that can happen because there is more opportunity to swap tokens. But really, what I mean by liquidity is like depositing tokens. So if a pool is deep in terms of liquidity, I mean that there is a large share, a large reserve of the deposited tokens.
So Kirill made the point here that the liquidity providers also face inventory costs. I think you can probably respond to that. I mean, I don't want to answer your question, actually, so maybe you should answer that, not me.
Yeah, the liquidity providers here, they just deposit tokens in the pool, and they are. I think that the question, we are not really looking at cost of holding inventory for those liquidity providers. So that's the only cost that they face, as we will show in this presentation, is basically the cost of not getting the same value of token that they would expect in case there are shocks occurring. And there is a question about, do you think LP tokens could be invoiced as securities? Yes. So I presume you mean the tokens that are being deposited by liquidity providers. Meaning, when you say invest as securities, my understanding that we are thinking whether or not they are definitely crypto securities because they are traded on the exchange, and whether or not they could mean you could have like tokens which are essentially very close to securities that you trade in traditional market, like fiat currencies. These are the stable coins, of course. So the question is, absolutely, you can think of them as securities, like just that they are securities that are trading on the blockchain.
Well, I'm going to disagree with you on this for a second.
Okay. Yeah.
I think we have to be very cautious when we use the term securities, because securities mean something very specific from a regulatory perspective, and there's specific regulatory implications.
Okay, that's good.
I think you can. One of the arguments, for instance, when you deposit in a contract, as I understand it, you actually get a receipt, so you can think about whether or not the receipt token that you receive, which you can then use for other protocols too, could be a security.
Yeah. I see.
The tricky thing.
The pool token, you mean, Andreas? Or
yeah, exactly, the pool token that you receive.
Yeah, exactly. The pool token could be used, in fact, for other transactions. I agree. Yeah, but I agree with you. There is, I think you made a good point that there are like regulatory concerns that distinguish traditional securities from.
I'm not sure if you want to answer or can answer this, but the one thing that I find really fascinating about this whole setup is, and there's a number of papers now that look at DEXs, and the function, the constant product function, which is the standard one that everybody has, is pretty much ad hoc. Do you have a sense of where it comes from, or maybe you want to tell the audience what you found of where it comes from, and because it is quite ubiquitous and for no good reason.
Yeah, no, I mean, I think the answer, I don't know the origins, but my guess is that this is a function which is for which it's very easy to compute the exchange rate, because if you want to understand like the rate that you exchange token B for token A, this is just the ratio between the derivatives, the function, and this ratio of derivatives is essentially B over A. So that's maybe one of the reasons why it's like a function which implements the convexity and at the same time specify an exchange rate, which is in a very intuitive way. It's essentially the ratio of reserves of one token versus the reserves of the other token. I don't know for sure whether or not this was the original reason, and if somebody has better ideas, I would be happy to know more myself as well.
Yeah, okay.
Yeah. I don't know if Roger wants to add anything in case he knows more the history about constant product function.
I'll just answer question in chat.
Okay, good.
I'm just gonna add, I think actually one of the origins is actually Vitalik. Vitalik had a blog post where he actually described this question, this particular function, and all things Ethereum related, if Vitalik says, oh, it's gold. Anyways, sorry, maybe I should. And this comes without criticism to him, obviously. But maybe we should just move on, and then you can continue with your talk.
Okay.
I should stop bantering.
Perfect. No, thank you, Andreas, for adding this. Let me go to literature review. I think it's important to point out that there is a literature on DeFi. I think it's an emerging literature, and of course I might have not included many of the papers, and I apologize for that. I mean, two papers which are more closely related to what we are doing here is one paper by Andreas, who is looking more at other type of arbitrage, like the front-running arbitrage, which derives from the fact that transactions submitted on blockchain are publicly observable and they can be front-run. There is a paper by Alfred and Christine as well, which is comparing centralized versus decentralized exchanges. There is a very large literature also in market microstructure on sniping risk and continuously method their book, in particular the paper by Budish, which which tries to come up with, which basically provides a mechanism which is related to the one that we have here, but there are like a lot of important differences that I want to clarify. And third, I think there is a very, very large literature on blockchain, crypto, and tokenization, which of course many of the people in this audience have contributed to. So let me go and discuss the model. I think this is a very simple model, which tries to basically make the point of why this arbitrage exists and why it cannot be avoided. We have 3 periods denoted by 1, 2, and 3. There are 3 types of agents. There are providers of liquidity. There are 2 arbitrageurs. So that's the minimum that you need to ensure that there is competition. And then there are liquidity demanders or investors. Investors are essentially those who want to swap tokens in the pool. And we position ourselves from the point of view of an AMM, where you are exchanging A for B tokens. The fundamental value of these tokens is assumed to be public information, so everybody can see and observe the prices of these tokens. Okay, there is no asymmetric information, there is no adverse selection in this model. The model works as follows. In period 1, the liquidity providers will decide how much to deposit into the liquidity market maker, how much to keep out. Period 2, that's where the randomness will occur. So we will have that token can be subject to price shocks, or investors can come and swap tokens, and investors can be of two types, type A or type B. So type A means the investor who extracts utility from holding token A. Type B is an investor who extracts utility from holding token B. Then at period 3, after these random events have occurred, there will be two kinds of arbitrage, which can be exploited by the arbitrageurs. The first is the so-called stale price arbitrage, and the other type of arbitrage is the so-called reverse trade arbitrage. And at the same time, where arbitrageurs try to exploit these arbitrage opportunities, liquidity providers try to withdraw their tokens to avoid being exploited. Okay, before I get to that, let me discuss what is the IMM pricing function. So that's like the function that the automated market maker will use to determine the price at each exchange token. So here we generalize from a constant product function, but we rather want to consider a more general convex pricing function with the only constraint, which is the AMM constraint. So the value of the function before and after the trade has to be the same. So if you have YA and YB tokens before the trade, then after the trade, if you deposit delta A token B and you take out delta B token B from the pool, the value of the function has to remain the same. Okay, so of course, as a special case, you have the constant product function, right? In this case, it's YA times YB. But there are a lot of other automated market makers in other decentralized exchanges which implement different form of the pricing function. They have essentially different convexities, and the complexity is needed because it's exactly the way that you use to capture price impact. And then what happens is that if we want to look at the infinitesimal exchange rate, so the rate at which you exchange token B for delta A in the limit where you basically deposit a very, very small fraction of token delta A in the pool, is essentially related to the ratio between the derivative of the function at X and Y, evaluated at the current state of the reserve in the pool. So that's why I was thinking that if we have a constant product function, if you differentiate with respect to X, you get Y. If you differentiate with respect to Y, you get X. So you get Y over X as the exchange rate, which I think is it might be one of the reasons why the constant product function is so appealing, because it's very intuitive to understand what an exchange rate is. So now I want to discuss exactly what is the problem solved by liquidity providers. So here is like one of the few slides where there is some mathematics, which is unavoidable because we have to set up the problem. We have n liquidity providers. Each of them has a positive amount of A and B tokens. So the idea is that EA and EB is the amount of token A and token B of liquidity provider I. And this token, part of this token will be deposited into the AMM, and part of this token will be taken out of the AMM. So Y is the number of tokens that are deposited, X is the number of tokens that are taken out. So then what the liquidity provider wants to do, he wants to determine how many tokens A and B to deposit into the pool in order to maximize his payoff, expected payoff at the end of period 3, after the arbitrageurs have executed their arbitrage strategy, if they manage to do so. So if you deposit in the pool, then the amount of token A that you have and the amount of token B that you have at time 3, which is denoted by YA with the superscript 3, might differ from the amount of token A and B that you have deposited initially, precisely because there have been a lot of events happening in between, including like shocks to the tokens and arbitrage execution. If instead you leave those tokens out, so X and XA and XP is the portion of tokens that you don't deposit, then nothing will happen to those tokens. You will keep them, and you just have to wait for the price, realization of the fundamental price at time 3. So that's how you evaluate the value of your portfolio. And of course, you have to take into account that you have to pay a fee in order to execute this liquidity. I mean, if you want to exit the pool or if you want to deposit in the pool. WI, this is also an important parameter, is the share of the pool. For example, if you have 2 liquidity providers, each of them holding the same share of the pool, then this WI will be equal to 1/2. So this is essentially the claim of the pool that you can that you have. The period 2 is the period where there is randomness occurring, and there could be 2 events, either a shock to the price of the tokens or investors coming. So the price shocks are like modeled in a very simple way. We have that the fundamental values of A and B tokens are subject to shocks of size beta. These shocks are independent. They are modeled like a Bernoulli random variable. So with probability P, there will be a shock to token A, and probability P, there will be a shock to token B. And if the shock happens, it's a positive shock. So that means that the price, the fundamental value of token A goes up, or the fundamental value of token B goes up by an amount beta. So that means that A becomes more valuable, or B becomes more valuable, depending on which of these two tokens has been hit by the shock. Or what could happen is that an investor comes, he will come with a specific probability, kappa I, and when he comes, he will extract private benefits from holding token A or from holding token B. So that means an investor of type A who comes, he will really extract an utility which is beyond the current fundamental price of token A. And the additional amount that he gets is alpha times PA. The idea here is that really if you are, let's say, if A is an Ethereum token and you really like an investor who like Ethereum tokens because you want to run, for example, the apps which require you to hold Ethereum token, then you will extract this extra benefit from beyond this fundamental value. Right? Same is true for type B investors. Okay, so now let's discuss what happens at period 3, which is exactly when the arbitrage takes place. There are two kinds of arbitrage that I want to discuss. Both are basically, both arbitrage originate from the fact that the fundamental exchange rate might be different from the exchange rate in the automated market maker. So the exchange rate in the automated market maker is the ratio of the pricing function at X and Y, as we have seen in the previous slide. The fundamental rate instead is just given by the ratio between the fundamental price of token A and fundamental value of token B. Okay. As soon as there is a deviation between those two, there is an arbitrage. So the first type of arbitrage is the so-called stale price arbitrage. So this means that if, let's say, token A is hit by a shock, that means that it becomes, if the shock is positive, it means that token A becomes more valuable than token B. But nothing has happened within the automated market maker because the exchange rate in the automated market maker only depends on the amount of reserves of token A and B that you have in the pool, right? Because that's essentially how we compute this derivative. But this means that if there has been a positive shock to token A, then I can go into the pool, swap token B for token A, and this will give me a profit, right? Because I am profiting from the fact that within the AMM, nothing has happened yet. But outside the AMM, like if you look at the fundamental, the price is higher. The second type of arbitrage is the so-called reverse trade arbitrage, which is essentially related to the fact that if, let's suppose that there has been a transaction up in the automated market maker, for example, an arbitrager has come and has swapped token A for token B. So we move from the red point on this curve to the blue point. Now, what can happen is that you could basically do the reverse trade, and essentially by doing this reverse trade, a potential arbitrager can earn or can profit because of the price impact that has been imposed by the earlier trade. So the idea is that you will basically walk back on this curve, and essentially you would be taking the spread. So the spread would be earned by the arbitrager who executes this reverse trade. It's not being earned by the market maker. So this is like a very important point, with I would argue also a very important difference with respect to the centralized bit of the book. But because in this case, who is earning the so-called spread, or maybe better, who is profiting from the price impact of the previous trade, are the arbitrageurs. Okay, so this I think this ends the model setup. I think it's a good, maybe a good point to stop and ask questions about the model before I discuss the results.
So let me ask a question then here.
Yeah,
my camera is off again. So I'm wondering for this. So when you, I mean, if you think about forgetting about the possibility there could be multiple exchanges, right? So
yeah,
if you buy, if I buy, for instance, if somebody bought from the market maker, right, from the automated market maker, say it's an uninformed trade, and then the price gets reversed by the arbitrageur, isn't it the case that what is the profit here that the arbitrageur has? Because the price ultimately after the arbitrageur makes the trade, at least under the constant product rule, would be exactly the same price as where what the fundamental value is. So where's the profit that it could make?
Andreas, to understand the question, you mean what's the profit that the arbitrager will make if he does the reverse trade?
Yes, exactly.
Right. I mean, I think the profit comes from the fact that somewhat the token A now are being traded. If you get back token A for token B, then you will be able to get an advantage you will be able to experience like a profit with respect to when you were trading before, because somewhat you are at this blue point in the curve, and it means that you could get many more token B for token A compared to what you were getting before. So essentially you can before you were getting like only 3.35 token, the difference between 10 and 6.7 token B, but now you are essentially getting more. So in other words, the investors have liquidity demand and they are pushing the price of one token higher. So that's the price impact.
Okay. Maybe I'm missing this, but we can discuss that offline. I just thought that when you say that you started the old position of 10.10 and somebody pushed the price to say, as you have 15 to 6.6, then if you trade back as the arbitrageur, then you still get 10.10 only. So it's not. So because I'm trying to say the price, the price that the noise trader has created is not a price at which you have a trade, because the return trade that you have is just at the fundamental value. But let's talk about that some other time. Maybe I'm just missing a part here. Just looking, there's no other questions that we have there. If there's no other questions, then why don't you just move straight into the results?
Okay, thank you, Andrea. And then happy to clarify more after after this. Let's see. Okay, this brings to the competition between arbitrageurs and liquidity providers. So the idea is that the profit of the arbitrageurs corresponds to the loss of liquidity providers. It's essentially a transfer of wealth between the arbitrageurs and the liquidity providers. So the arbitrageurs are basically gaining from what the liquidity providers lose. And really, the execution of the arbitrage can be seen as, let's say, a first price auction, meaning if you are the first to execute the arbitrage opportunities, there are two of them, two arbitrageurs, only the first arbitrageur will gain, and the second arbitrageur will get nothing, right? So that means that if we do not buy, say, pi, the maximum revenue that an arbitrageur can get from executing this arbitrage trade, then by competitions, both arbitrageurs will beat pi, right? Because that's exactly, they will bid up to the maximum amount they would gain from the trade, right? And because they will make pi from the trade, they are willing to bid up to pi. So in a way, de facto, these revenues are being all passed to the miners, right? Because of competition, the arbitrageurs will basically extract zero profit from this, and all the revenues that are entailed by these transactions are being passed by the miners to the miners in terms of fees. But arbitrageurs will bid pi, and now somewhat what can the liquidity providers do? So each liquidity provider is only bearing a loss which is proportional to the amount of share that they have in the pool. So if they have a share WI, then how much they will lose is WI times pi, right? Because they only hold, let's say, if WI is 1/2, they only lose a fraction of the entire revenue that the arbitrageurs are making. So this means that they will be willing up an amount which is at most WI times pi, because there is no reason for them to bid higher than that. Otherwise, they will be paying a fee larger than the loss that they are trying to avoid. So in other words, because WI is smaller than 1, the fees that is paid by the liquidity providers is always smaller than the fees that is paid by the arbitrageurs who are competing. In a way, this means that this arbitrage is unavoidable, right? Because the liquidity providers basically will have zero incentive to bid higher than pi. And just because by the design of the market maker, right, which is essentially a mechanism where liquidity is pooled, so everybody holds only a fraction of the entire pool, while the arbitrage is being conducted against the whole pool, right? It's not, I'm not arbitraging only one liquidity provider, I'm arbitraging the entire pool. So this is exactly the reason why this arbitrage becomes unavoidable, and therefore they can extract the rent from the liquidity providers. Okay. So now I want to to relate this to the sniping risk in the limit order book, because I think there is an interesting analogy to be made. And the idea is the following, that if we think about limit order books, like there is a paper by Budish, Crampton, and Shim, which basically shows that there are arbitrage problems which arise because of symmetrically observed public information. So there is not symmetric information in their model, but simply what happens is that there are like trades that are executed. For example, you want to swap a token for me. In their case, they want to swap Uniswap contract for exchange traded funds, and they say, okay, if there is a shock to one of those pairs, to one of the elements of this pair, for example, the mini future contract are shocked positively. So what happens is that the liquidity providers would like to send an order to the exchange because they would like to update the state quote. They want to notify the exchange that now the quote needs to be updated and the new exchange rate should be modified. But at the same time, there are trading firms which want to snipe somewhat the order book, and they would like to profit of this state quote so that they can earn profit by executing transaction at the state prices. And the idea is that if they are faster than the liquidity providers, if they are able to like enter into if they are able to send the order before the liquidity providers try to exit, they will essentially arbitrage them away. And this is essentially due primarily to the latency. So the latency here plays a fundamental role. So the idea is that the liquidity providers are not fast enough to exit. And this problem, which arises in a continuous time serial processing market, can be solved if you take into account the frequent batch auction, which is the solution that they propose in their model to prevent this from happening. So here, like the friction is not really the latency, but it's really the execution fee, the fact that on blockchain, you have an order priority, which is determined entirely by the fee that is paid. So it's not really a competition on speed because every block is mined every 10 seconds, right? Roughly in Ethereum, but it's really about submitting a fee which is large enough. And the second point where this arbitrage order is because there is this liquidity pooling. So you only hold one share of the pool, a limited share of the pool, you don't hold the entire pool. And in order to fix this problem, what we propose is essentially a mechanism which is acting on the convexity of the pricing function. So how can we choose a pricing function which mitigates this arbitrage problem? And that's I want to show how this convexity is really the idea behind the V3 version of Uniswap. Okay. Let me move on to the next slide, which is basically giving the important result, which is about the adoption of the market maker. And here we have that liquidity providers are facing essentially a fundamental trade-off between revenues from trading with investors and rent that is extracted from the arbitrager. So this is really the key trade-off. On the one hand, you want to incentivize enough trades because you profit from the fees paid by the investors. On the other hand, you are worried that there is too much rent which is extracted by the arbitragers. And what we show is that there could be a situation where there is a liquidity freeze, where again, liquidity here means that no tokens are deposited in the pool. And this occurs even though if the price shock is sufficiently large. So the idea is that this price shock is related to the volatility of the log of the token exchange rate. So one could basically draw these analogies. There is a large price shock. It means that there is somewhat more volatility in the exchange rate. And of course, this also means that there is more profits to be made by the arbitrage, by the arbitrager, because if there is a larger shock, he will profit more from deviation from the sale price arbitrage. And this threshold is also increasing in the trading volume. So alpha and kappa, remember, are essentially the utility that the investors get from trading and also the probability at which they come. So if there is more trading volume, on average, trading volume goes up. That means that the revenues paid by the investors are larger and therefore liquidity freeze is least likely to occur, right? That's the idea. So in other words, like this arbitrage problem is unavoidable because of the current design of the exchange. And I also want to relate this to me. I want to find another important characteristics, another consequence of this competition done by the arbitrageurs in a situation where there is no liquidity freeze, which means that the liquidity providers are depositing tokens. We see that the expectation and variance of the gas fees that are bid by the arbitrageur are increasing in beta. and they're also increasing in the amount of deposited tokens. So that means that if the shock size is larger, or if there are more deposits, if the pool is deeper in terms of number of deposited tokens, then liquidity freeze is then the arbitrageurs will extract more profit, and therefore they will have an incentive to bid higher fees, right? Because there is more rent to be extracted. But this, of course, has negative consequences for other users of the same blockchain, because if you want to either transact on the blockchain, or if you want to enter the blockchain, you will be discouraged from doing so because you see that the fees are really large, right? So that means, and this is also one of the reasons behind using sharding, which is essentially segmentation of the blockchain so that you can compartmentalize in a way the blockchain depending on the type of transactions that are being executed, exactly to prevent that you might have to wait forever, or you might have to bid larger fee to get executed. Okay, so this leads me to we have identified this problem. Now I want to discuss how can we propose a solution for this problem. And I want to discuss just a simple idea that can be used to control the extent of the arbitrage rent that is being extracted. So we have essentially the on the right graph here. I'm considering two different curves. One is the Uniswap constant product function, and the other one is the constant spot function, which means the straight line. So in the straight line, basically means that you swap exactly at the rate which is determined by the slope of this line. So if we think about the linear function, there is no price impact here, right? Because there is no convexity. So that means that you don't incur any cost when you execute. Of course, if we think about the dotted line, the constant product function, that will have price impact because of the convexity. So now what about taking somewhat a combination of those two, let's say an interpolation between these two curves or a convex combination of these two curves, and see whether or not there is some level of convexity which mitigates this arbitrage rent, which minimizes somewhat the arbitrage profits that are being made by the arbitrager. And the idea is the following. So on the one hand, we could choose a very small convexity. For example, we can go towards the idea of having a linear function with a straight, just with a slope and no convexity. But the problem is that if we do that, there will be, of course, very, very little price impact, which means that the arbitrageurs will be incentivized to trade more, right? Because really, the arbitrageurs face this problem. On the one hand, they want to profit from the price deviation between the fundamental and the spot rate within the automated market maker. But also they are concerned because their trade will be subject to a price impact, right? If the price impact is too large, of course, maybe it exceeds the profit that they would make from this deviation between the two rates. But if the complexity is very small, if they incur, for example, zero price impact, then as soon as there is a token price shock, no matter how large it is, they will immediately trade and extract rent. So that's bad, right, for liquidity providers. But on the other hand, the investors will also trade more, like liquidity demanders will also trade more because they incur low price impact. So they will swap more. Now, what happens if you have a large convexity? It's a little bit the reverse. If you have a large convexity, price impact is large. That means that the investor doesn't want to trade much. Therefore, he will not be providing a large revenue in terms of fees to the liquidity providers. But it's also true that the arbitrageurs will be extracting smaller rent because they're also disincentivized from trading, exactly because they are incurring large price impact costs. So that's basically that basically calls for designing an optimal convexity. So in other words, can we identify a level of convexity which is optimal, which is not too large or not too small? And the idea is that we want to reduce the arbitrage rent, but at the same time, we want to maintain enough flow. So we want to guarantee that investors trade and they provide a large amount of fee revenue. At the same time, we want to prevent a large arbitrage to be exploited. So the expected payoffs is maximized at this optimal convexity, and the occurrence of a liquidity freeze is minimized. So that basically is the idea of, if we are able to compute this optimal convexity, that means that that's the point exactly where liquidity freeze is least likely to occur, because this maximizes the payoff of liquidity providers. Okay. And one can characterize exactly this optimal level of convexity by looking at those two functions. So now I want to discuss how this convexity is related to the V3 version, or the version 3 of Uniswap. So let me first explain how the version 3 of Uniswap works. So what I've been discussing, like if we look at the cost and product function that I have illustrated before, this is how liquidity is provided and how pricing are determined according to the version 2. In version 3, what happens is that the liquidity providers can choose exactly what is the interval of the curve at which they want to provide liquidity. For example, B here is the maximum price at which they are able to allow for a token exchange, and A is the minimum price at which they are able to support a trade. So this basically prices are given by the tangent lines. And then after specifying the minimum and maximum price at which to provide liquidity, which is equivalent to specifying the interval on this curve, we want to maintain exactly the same shape of the curve that we had in Uniswap v2. And this basically leads to this line, this yellow line here. So this yellow line is exactly as the same as specifying that you provide liquidity only up to a maximum amount of exchange prices and at a minimum amount of exchange prices, and you maintain exactly the same shape that you had before. Bottom line, the liquidity provider are choosing exactly the interval at which they want to provide liquidity. Okay, so the interval pins down the shape of the curve, but how large this curve is depends on how many deposits are there, right? If you deposit more X and Y reserve, then you will have a larger size of the curve, right? For example, if you look at these red dots, you see that if you have red dot corresponding to a larger amount of X and Y deposits, this pins down a larger curve. So you are providing liquidity on a larger segment of the curve, right? So the interval is pinning down the shape or specifying the minimum price and the maximum price at which you provide liquidity. And the amount of deposit is determining how large this curve is, so how much trade there could be. Now, I want to compare this with the V2 version of the version 2 of Uniswap. So as I mentioned before, choosing an interval is essentially the same as choosing the convexity of the curve. Why? Because basically the larger is the interval that you pick, and the larger will be the convexity of the curve. Now, if we want to compare like Uniswap v2 with Uniswap v3, let's think about a liquidity provider which is depositing an amount of X and Y reserves, which corresponds to this blue point on the curve, right? So the amount of deposit is fixed both in one case and in the other. Now, what we see here is that for the Uniswap v2, you have the green curve. For the Uniswap v3, given this amount of deposit, you have exactly this yellow curve. And you can see, right, from this that the yellow curve has a smaller convexity of the green curve, right? So having specified an interval brings you a smaller convexity. Sorry, and just to reinforce this point further, the smaller the interval that you pick on the curve, and the closer you get to a straight line. So the smaller the convexity of the curve becomes. So if you choose A and B here, you have somewhat the yellow curve. If you choose intervals which are smaller, for example, A prime and B prime, you see that you get this red curve here. So which is almost like a straight line. So in the limit, if you make B and A closer and closer together, you are essentially converging to the tangent line, right? And this means that you are essentially getting a straight line. And essentially the result, so the idea here is that Uniswap v3, the liquidity providers, by choosing the interval, are essentially choosing the convexity of the curve and also the size of the curve by specifying how much to deposit, which is essentially related to what I was arguing before, that in Uniswap v2, you could control the convexity of the curve because that's what really determines the extent of the arbitrage. Here, you can do essentially the same. You can control the convexity of the curve by specifying an interval at which you provide liquidity. And yeah, and this essentially brings me exactly to the fact that choosing convexity means larger interval, larger convexity. Larger convexity, of course, means more price impact, which means smaller trading volume. And of course, this has an implication for the arbitrage loss, right? Because there will be also less loss that is extracted from the arbitrage. But on the other hand, you also have to take into account that because the price impact is larger, there will be less trades done by the investors because they will be discouraged for the price impact. Okay, so now how do we map this to the statement, to the result that we have in the paper? For example, if we think about stable pairs, so these are AMMs which are handling a pair of tokens which are both stable currencies or stable coins, sorry. So stable coins means, for example, in this case, USD coin and DAI. These are like stable coin pegged to currencies, fiat currencies. And the idea is that if we think about stable pairs, the volatility here of the token pair is small, right? So that means that the arbitrage problem is not very severe, because if you remember the result, the arbitrage problem becomes severe when the shock is large, which means that there is a larger volatility for the token exchange rate. But in this case, that's not the case. And in fact, if we think about if we look at this histogram, which is basically specifying the amount, I mean, for a specific pool, how much liquidity is provided for that specific price, we can see that they are only providing liquidity in a very small segment of the curve, right? But if you compare this with unstable pairs, where the arbitrage problem is more severe, for example, and this is a pool where Bitcoin are being swapped for Ethereum and vice versa, you see that the range of prices for which liquidity is being provided is much larger, right? And this is essentially consistent with the fact that for the unstable pairs, then you are really worried about the arbitrage rent. So you want to specify a curve which is really not too convex. Yeah. And so this basically brings me to the next point, which is if we want to alleviate this arbitrage problem. So one possibility is to act on the convexity of the curve, either directly on Uniswap VT by choosing an optimal convexity, or Uniswap V3 by specifying the interval at which you decide to provide liquidity. Or one could argue, okay, what if we pool multiple tokens? What if instead of having only A and B, we have A, B, and C? For example, we could, why not implementing a product function which basically computes the product of amount of token X, token Y, and token Z, right? You don't have necessarily to handle only two tokens. Right now, most of the MMs are handling 2 tokens. As far as I know, all the MMs are handling pair of tokens, but in principle, you could think about allowing for different type of tokens as well. So you could have Bitcoin, Ethereum, and for example, USD coin in one AMM and implement a constant product function. The question is, do we think that this is going to alleviate or mitigate the arbitrage problem? I mean, implicitly, I think what I've been talking to a few practitioners who are like managing these AMMs, or they are involved with the design of the AMMs, and most of them, I think that if you have more tokens, then you have also benefit coming from diversification, because the shocks, like the probability that the shock will hit one specific token becomes lower because you have more tokens which could be subject to these price shocks. And the idea is that pooling more tokens, actually what we show is that they exacerbate the arbitrage problem. So the idea is that if you only have 2 tokens, then you can only profit when you have an arbitrage, you can only act on swapping the least valuable token for the more valuable token, right? But if you have more tokens, for example, you have token A, B, or A, B, and C, suppose that B is hit by a shock, then you could basically start swapping B for A, because like B is the most valuable token, and you want to you want to trade A and get B. And then what could happen is that at some point the marginal benefit of keeping exchange B for A goes down. At that point you could start swapping B for C, right? So for example, you want to get rid of B is the token that you want to get rid of. You can say basically first, that you want to get. First you could get A for B, and then when you see that the marginal gain of getting A for B goes down, you will switch to C. So in other words, you have more possibility, you have more options to to exploit in order to get the more valuable token out. And I mean, the other end, so this is basically means that for each arbitrage opportunity, the arbitrager can extract a larger portion of the shock token using the deposit of the AMM. So what we show in the paper is essentially that the arbitrage gets worse once we take into account AMMs, which manage more than 2 tokens. And I think at this point, I might stop because what is coming next is just the end where I discuss the empirical implications of the model.
Oh, okay. Thank you for that. So there was a question here, which I thought would be probably beneficial if you still address it. So it's from Francisco from the Bank of Canada. And he asked basically whether or not each combination of the A and B token that people create would be a new pool. And so maybe you could just speak for a moment as to how Uniswap, for instance, aggregates the various different functions and how you do this within your model.
Yeah, right. So essentially, Uniswap aggregate all the pools, but when the liquidity demanders trade, they essentially trade at all pools, providing liquidity at the price range.
So in many ways, one could think about this probably, I mean, so if we think of an economic model that we would propose, right, where you have liquidity providers, they would provide a function, right? So what they do is they have a demand supply schedule, and then that gets aggregated.
Yeah.
So now, in many ways, actually V3 and also what you propose is going much more into that direction, right? Because so you know, when you have the constant product function, that's okay, that's completely exogenous. There's one variable that you can pick, which is the total amount of volume of liquidity that you provide, right?
Yeah, exactly.
Right?
Yeah, exactly.
Whereas here you have this range, right?
Yeah.
So really what you, so.
No, go ahead, exactly. Yeah, in the end, here you have this range exactly at which you provide liquidity, right? And this is basically specifying, I mean, is allowing you to determine whether or not you want to get more or less liquidity, like depending on the size of the deposit that you deposit, the amount of deposit that you make, as well as the interval at which you want to provide liquidity. So if you specify a very, very small range, then you will basically be able to support liquidity only for a very small number of trades, like if you don't deposit much. But if you want to provide liquidity for a larger segment, then you end up more as Uniswap V2.
So now maybe I've missed that actually in the model description. So what I'm trying to figure out, if I would be thinking about this as a model, what the ultimate trade-offs are, right? So there is the information content, right? And so that's the first part, and then the second part is the size of the noise order. Are these fixed in both cases? So it would be really here, you know.
So you are saying, Andreas, on the comparison between 2 and 3 tokens?
No, actually, just generally speaking, that is already just on the one, right? So when you're thinking about how you want to, so this particular function, right? So what's the trade-off what is the trade-off that liquidity provider looks for?
Okay. So if let me clarify. So if one wants to design a model, maybe that's best in here. So if one wants to design a model on Uniswap V3, then I think the key decision variables for the liquidity providers would be the interval at which you provide liquidity, so A and B, and how much to deposit, because how much you deposit initially. By specifying an interval, you are essentially deciding on the convexity of the curve, right? And by specifying, and you are deciding, on the minimum price and the maximum price at which you provide liquidity. And then by specifying the amount of deposit, you specify which is exactly this red point here. You are deciding on how large is the range of trades that you can support. So you basically specify interval and amount of deposit that you want to give to the AMM initially. This pins down exactly the convexity, the shape of the curve, and the size of the curve. This will be essentially, if one wants to set up an economic model, and the trade-off that arises in such a model would be similar to the one that I've illustrated before in a way, because if you decide on a very large range of, then you will still be subject to like more arbitrage opportunities because there will be larger, you will be subject to less arbitrage opportunity because the complexity will be smaller, will be larger, right? The larger is the interval, the more convex the curve will be, right? If you make A and B even further apart, you choose A in this further on the extreme right of the curve, then the complexity will be larger when you project this curve on the XY axis.
Okay.
And similarly, if you choose a very, very small interval, you will get basically almost a linear function. And therefore, you will have very little convexity, so very little price impact. So more trades coming from the investors, but also more arbitrage rent that can be extracted. So in a way, it's a similar trade-off, right? You have to deal with like this trade-off between arbitrage rents and investors' trades. It's just a different way of specifying the convexity. So instead of acting just on the Uniswap V2 curve, you could say, okay, let's take the Uniswap V curve as given. It could be the constant product function, and let's just modify this convexity by picking the points on the interval, by picking the point on the curve, by specifying the interval of the curve.
Okay.
Does it?
Sorry. Go ahead.
No, I was thinking, does it answer your question, Andreas?
Yes, it does. Thank you. So before everybody, so I know that you still have a few slides to say, but because some people may already dash off for lunch, I just want to take this opportunity just to promote quickly the next event, which unusually is actually not in 2 weeks, but is in exactly 1 week on March 17th, again at 11 a.m. Eastern time. Please, for those of you in Europe, keep in mind that we change clocks this weekend and you change them 2 weeks later. So this talk will be about auditing economic mechanisms in blockchain protocols. So in other words, do smart contracts work economically the way we intend them to? So with that quick reminder, maybe Agostino, you could just wrap up with your empirical portion of your paper.
Yeah, right. So the final point, exactly. So the empirical portion is essentially, we tested these main implications of the model, which are essentially one, that if there is more volatility in the token exchange rate, this is decreasing the amount of tokens that are deposited at the automated market maker. Like I've shown the extreme case where you have liquidity freeze, but as the exchange rate volatility goes up, the amount of tokens deposited would go down. That's what the model predicts. And also, if we have more trading volume, in terms of the model parameter, means that investors are more likely to come or they extract higher utility from their trades, then the amount of token deposited at the automated market maker would also go up. So that's exactly because of the revenues from fees goes up. And also that the gas fees are higher for more volatile pairs. So if we think about unstable pairs, there will be higher volatilities of gas fees. So what we did was we collected data containing essential history of all trades. And these trades are both swaps, deposits, and withdrawals. For 24 automated market makers, 13 of them are from Uniswap V2, and the rest are from SushiSwap. And among those 24, we have that 4 pairs only consist of stable coins pegged to $1. And these are the ones that we know by stable pair. So a stable pair is a pair of tokens which are both stable coins. And then we estimated the volatility of the token exchange rate using data from Binance, like centralized exchange. So these are just like regression results that we get where we are regressing the inflow or outflow of deposits versus volatility of token exchange rate and trading volume. So what we see looking at the coefficients of the regressions, that basically higher exchange rate volatility reduces the amount of tokens that are deposited, consistent with what we expect from the model. And also, if there is more trading volume, the flow rate also would go up. Right? And these results are both statistically significant, as you can see from the columns, but they are also economically significant because if we look at one standard deviation increase, for example, in the exchange rate volatility or in the trading volume, as basically corresponds to a large number of standard deviation increase also in the inflow rate of deposits. We also looked at volatility and prices of gas fees. And here we exploited the segmentation of the MM in terms of stable pairs versus unstable pairs. So if we have a stable pair, we see that both volatility and the price the gas price would go down, and they go down also by a significant amount. So if the volatility goes from 179 to, goes down by an amount of 111, so it's like over 50%. And also the level of the gas fee would go down significantly. So this is actually supporting evidence that if we think about stable pairs, the externalities that are imposed in terms of gas fee on other users of the same blockchain are smaller, exactly because there is less competition from arbitrageurs to exploit those opportunities. And this brings me to the end. Essentially, the main point was to show exactly why and when liquidity freeze can occur, why liquidity providers might be exploited and therefore not depositing tokens in the first place. And we have seen that the main reasons is exactly due to the order execution mechanism of blockchain, where transactions are prioritized based on the fees that are submitted, and the fact that liquidity is crowdsourced, and therefore every liquidity provider only loses a portion of the entire, a portion of all the arbitrage that is being executed against the entire pool. And if we have larger volatility for the token pair, or if we have higher trading volume, then we see that liquidity provision will have different, or depositing of tokens will have a different effect. So it will go down if tokens are more unstable, and it will go up if there is more trades by investors. And one way to control the problem, or to mitigate the arbitrage problem, is to act on the convexity of the pricing curve. And as I've shown, acting on convexity can be done either directly by specifying a suitable automated market making function in, say, Uniswap v2, or you can, if you think about v3, you could try to pick or pin down the convexity by specifying the interval at which you provide liquidity and the amount of tokens that you deposit initially. And this brings me to the very end.
Well, thank you so much, Agostino. This was great.